Yeah, so now we are recording. So, any questions from the last week? So last week we saw text data analysis, and our capstone project is on text data analytics. So, this last week's content was very much needed in our capstone project. So, any questions there? So, we'll be touching back again most of the concepts in the capstone project. But any big questions you have from last week? Anyone? Okay. So we finished actually on the supervised learnings algorithms in machine learning. Not all of them, but some of them are most important one of them. And today we'll be doing unsupervised learning. So you guys remember what was the difference between
Rohit, there is one thing. Last session also I requested. Um, although this content is really good, but in order to understand what all, in order to summarize, basically, not understand, in order to summarize all the models, all the algorithms which we have gone through, um, is it possible at your end to share one or two slides on that, that these are the supervised learnings we have seen, gone through, and these are the algorithms we have seen in that, and these are the, you know, uh, this is the basically, um, these are the areas in which these algorithms has been used as a known scenarios, widely used. Means I understand that it's very difficult to uh, say that which scenario is best for which algorithm, because we have to test each and every one. But still, one or two pages on that, because I find that machine learning is the gist of whatever we have been learning in this course, because that is really important. So is it possible that that summary can be shared with us?
yes, so I already asked some of the senior content creator people from Digit and Vidya to create this, and they propose that we do this along with some exercises. Okay, we have special use cases data along with the machine learning to show you also that okay, this kind of data, this machine learning is performing better and why and all these things. So we are preparing that.
Why I'm asking, because when we go in industry, we should be very clear about when someone is talking, we will be easily able to correlate it if we have that much of understanding on it. So we can understand that our mind will start processing that these are the uh, problems, statements which can fit well in these kind of algorithms. It's just a discussion. It will help us in discussing more about proposing any solution to our clients during those discussions. And later on, eventually, it doesn't matter that how the complete solution has been given and designed, but during those discussion sessions, it really helps us.
Yeah. Yes, and so actually we already talked about this last week, and they are preparing this new content. I will share with you as soon as it's done.
Sure, sure. Thank you very much.
Yeah. Okay, sir. So yeah, so this week's we are starting unsupervised learning. So I hope everybody remembers the difference between supervised and unsupervised learning. Any yeah others? Nitish, Sonia. So just a recap, if you guys are a bit confused of what was the unsupervised learning. Not We don't call it inputs. We don't have the labels of the output. So, for example, let's take the iris data set we had, and so you have sepal length, you have sepal width, you have petal length, petal width, and then you have the name of the species. That okay, it is setosa, or it could be, I think there were 2 or 3 species. Okay, and then the task was to build a machine learning model which, given sepal length, width, petal length, and petal width, could predict what is the name of the species. Okay, and on this it was considered supervised learning because you knew already for each feature what is the output label. Okay, what is the class. Okay, so this is supervised learning because you know the relationship between input and output, and then you learn from that. Unsupervised learning is where you will not be given these pieces, you are given just these inputs. That okay, they are, this is the separate with pattern and pattern with, that's all, and the species column is missing. Okay, and then you are asked that okay, how many species are there? Could you find out okay how many different species of flower, I think it's flower or plant, is there? Okay, so this is unsupervised learning where you don't know beforehand the mapping between these features and what is the output. Okay, so there are two main clustering. So mostly in unsupervised learning, you do clustering problems. Okay, so you want to find the groupings. Okay, how many different groups are there? And you, because you don't know already, okay, which who belongs to which group, so you find okay how many groups could be there and who then belongs to which group. And then maybe you could ask some expert to name those group. So naming the groups is done by some domain knowledge experts. But being a machine learning guy, you would be only able to find out what they are groups and how the groups are formed. Okay. So the most popular unsupervised learning is the k-means clustering. Okay. So anybody has heard of k-means clustering before? So let's start with some. Okay. So how k-mean clustering works is, suppose this is your data points. Okay. So first of all, k-mean clustering will work on a Euclidean space. Okay. So it considers, it's like the k nearest neighbor. Okay. Where if you remember in k nearest neighbor, we used to find out that okay in which class they fall is okay the maximum of the neighbor classes, right? And how you find neighbors? You find neighbors based on the distance, the Euclidean distance. You could use other distance measures, but okay, mostly it's Euclidean distance, Euclidean space. Okay, so suppose these are the different data points you have. Okay, in 2 dimensions, so the number of dimensions are 2. It could be n dimensions. So the concepts of dimensions are clear, I hope. Or we call them features or dimensions, right? So in this case, there are 4 dimensions if we consider these 4 parameters. So these are the 4 features, and these are 4 dimensions. Okay. So suppose in this space, these are the points, and now you have to cluster them. Okay. So you want to try them to group them. Okay. So you say, okay, let's assume somehow we knew that there are 3 classes or 3 groups. How we can find how many groups were there is we can see later. There are methods to do that. So let's assume you already knew that in this data there are 3 groups. Okay, and so you want to find out these groups and put all these points into their respective groups. So how k-mean clustering will work is, okay, so you will start, if k is 3, you will start with 3 randomly chosen positions. So suppose we chose these 3 random positions as the 3 groups, the center of the groups. Okay, so they are called centroids or cluster centers. Okay, now for each point, you see the points which are close to it and you form them into a group. So from this blue, you see, okay, these 4 are the closest one. So this is one group. These 4 are closest to this one. So this is one group. These 4 are close to the green one. So this is one group. So you say, okay, this is your cluster. So this is the first step in k-mean clustering. So you take 3 random, for k is equal to 3, you take 3 random points, then you assign each point in the space which is closest to one of those points in that cluster. Then now for each cluster, so suppose this is the first cluster, this is second cluster, this is third cluster. For each cluster, you find a new point or the centroid. So earlier these were the random selected centroids of the cluster. Now the clusters are formed. Now for each cluster, you find the new centroid or the new center of the cluster by taking the mean average distance between these points. And suppose this is the cluster. When you take the mean average distance, the center of this cluster move from here to here. Okay. For this cluster, suppose the center didn't move. It was by surprise or somehow you find a good cluster center, it remained there. And for green one, it moved from here to here, depending on this 4 points. Now you again do which are the closest ones and create new clusters. And it turns out, okay, now this cluster remains same. This cluster has only 3 points now. And this point which was earlier belonging to this cluster is now belonging to this cluster. Okay. So now this is the new cluster configuration. This is step 2. And these steps you could go on repeating. So now again, for this cluster, you will find the centroid again. So this point can't move here. And this point may move here a bit. Okay. So the new center or centroid of the cluster would be calculated based on the distances between the points in the cluster. Okay. So what is the mean distance, the point of the cluster? And again, the points would be assigned to those clusters based on the distances from this new centroid. And this process will keep going till either two conditions are met. First, while you are running the algorithm, you will say, okay, don't do more than 100 steps. So after 100 steps, it will stop. Or when the center stops changing. So if the centroid will not change anymore, then the algorithm will stop. So these are the two stopping criteria for the k-mean clustering. So it's very simple algorithm, and this is how it works. So at the end, you get the desired clusters. So is the description clear? We'll take one example also now on one dimensional space. So suppose, let's take one example. So suppose you have only one dimensional space and your points are 2, 4, just give me some numbers like 7, 18, 22, 43, 54, 65, 3, 8. Suppose these are the points. Okay. Now I ask you to, okay, these points which is in a one dimensional space, divide them into two clusters. Okay. So first, what is the first step? To take two cluster centers at random. So give me two numbers at random, any two numbers. Anyone? So 18, 43. So it doesn't have to be numbers from this list, okay? So it could be any number. So the numbers doesn't has to be this in the first cluster center which you decide doesn't have to be one of these data points. So it could be any other point. So is that clear? Because this is one of the confusion people have, that okay, the cluster points has to be one of the data points. It doesn't has to be. Okay, so you could very well assume 10 as one center point, 40 as another center point. Okay. So now there are algorithms and other techniques which we'll not be discussing because it's too mathematical on finding the initial seeds center points so that the number of steps required to converge is fast. Okay. But that has nothing to do with the k-mean algorithm. So k-mean algorithm will work for any number of any random centroid. Okay. So suppose we took 10, let's keep 43 as Sonia mentioned. So we take one of Sonia's and I will propose one. So 10 and 43 suppose. Okay. So which numbers will be in cluster 1 and which will be in cluster 2? So 2 is more close to 10, right? So 2 would be in cluster 1, 4 would be in cluster 1, 7 would be in cluster 1, 18 would be in cluster 1. Okay, 40, 22 would be in which cluster? It's one dimensional space, so distance is just the difference. So 22 is more close to 10 or 43? Yeah, 43 is here. 54 is more close to 43, right? 65 also would be here. 3 would be here. 8 would be here. Okay. So these are my two clusters. So this is step 1. Now step 2, find new centroids based on the average distance between the on the elements in the cluster, right? So for here, what is the average distance? The midpoint for this cluster would be sum of this divided by the number of elements in this, so which would be 2 plus 4 plus 7 plus 18 plus 22 plus 3 plus 8 divided by 1 2 3 4 5 6 7. So 9.14. So now my new centers are 9.14 and other center is 43 plus 54 plus 65. 162 divided by 3 is 54. So these are my new cluster centers. Now I have to repeat again the same step. I have to form cluster 1 and cluster 2. So again 2 is will be in cluster 1. I think nothing will change, all of them remain same. 2 will be here, 4 would be here, 7 would be here, 18 would still remain here, 22 would remain here, 43 would remain here, 54 here, 65 here, 3 here, 8 here. So the cluster didn't change, right, based on the new center. So now the algorithm will stop automatically because it knows the cluster center. Now if you calculate the cluster center again, it will be 9.14 here, 54 here, and the algorithm will stop. But if you would have started with some other points, suppose you would have started with m1 is equal to, I don't know, 1, and m2 is equal to 10, then the number of steps required to stop would be different, right? Because now the cluster 1 would be, okay, 2, 4, cluster 2 would be 7, 18, 22, 43, 54, 65, 3, 8. What would be the new cluster centers now? Who can tell me? New cluster centers for these clusters. Okay, m2 would be, so you need calculator. 31. Can someone else validate? Right. So now what would be the new clusters based on this new cluster centers? So 2 will be here, 4 would be here. Now 7 would move from cluster 2 to cluster 1. 18, okay, 31 minus 18 is 13. And 3 minus 18 is 15. So 18 would be here. So 22 would be here, 43 would be here, 54 would be here, 65 would be here. 3 and 8 would be here. So is it clear now how this algorithm is working? Now again you have to calculate cluster centers. It will again change. So now cluster centers would be 24 by 5, 4.8. How again the C1 and C2 got cleared? So now your cluster centers are 3 and 31, right? So again you will do the same thing. Which numbers are close to which cluster centers? So 2 is close to 3 or 31? 4 is close to 3 or 31? Yeah. So you start with random cluster centers, assign clusters, so which are close to that center of that cluster. So earlier these were close to the cluster center and these were close to this cluster center. So now this is a cluster, this is a cluster. Now for each cluster you find again the cluster center based on the elements on that cluster. So now these are the next new cluster centers, and then again you form clusters based on, okay, which number is close to which cluster center. So you got this cluster now. Again you will find cluster center for this cluster. Okay, and you can keep going it till the cluster center is stopped changing. Like in this case, when we started with m110 and m243, after second step the cluster will not change anymore. Okay, and this will also converge somewhere here. and it will inform these two clusters after a few number of steps. Okay, so this is how k-mean clustering works. I think in two more steps, this one will also stop. So it doesn't matter from which random state you start. Unless there are too many data points and you have upper criteria when to stop. Okay, because it could be the case that you have done 100 iterations and still the cluster centers are changing. Okay, and you might need 10,000 steps to converge. But you have, in the algorithm, you will specify how many iterations you want to do. So if you say, okay, stop after 100 iterations, suppose. Okay, so is k-mean clustering clear? Others, Sonia, Nitesh, questions? So let's go back how to do it in Python. So no, which one you think it's similar to? So it's a distance based method. So if you remember, there is something on k nearest neighbor in supervised learning, but there you already had the classes. So here you don't know the classes, so everything is in the same color, right? In k nearest neighbor, each point already has a case assigned to it, so each point will have a color assigned to it, that okay, which class it belongs to or which cluster it belongs to, because it is supervised learning. Then given a new data point, you find okay, which is the class of this data point. So you find out the nearest elements to that point and what is the maximum number of classes to the nearest k neighbors, and that point is now belongs to that cluster. So it's supervised learning. In k mean clustering, which is unsupervised, you don't know the cluster, the colors of these points or which class it belongs to, so you try to group them together. And once that is done, so this center points is now then used for new classes. So once you have, suppose this is your final cluster you have decided and these are final center points, when a new point appears somewhere, you compare that distance from the cluster centers and the nearest cluster center it is to that class, you assign it to that. Okay, so let's use our iris dataset. So first let's visualize pattern length versus pattern width. So this is how the scatter plot of pattern length and pattern width are. Okay. So to use k-mean clustering, you have to, this is what you have to import: sknuns cluster. Okay. So again we are forming our x and y coordinates. Y is your uh, group, cluster group. So this is the same data set, but here instead of these species setosa, they are mapped to 0, 1, 2. So there are three species 0, 1 and 2. Okay, so now let's start. So we'll not use this y right now, we'll use it only to test. So we just use the x. Okay, so we don't have an input variable, what we have is just x, the data. So you create a instance of the class of k means, you say number of clusters is 3, random state is 0. So based on this random state, the initial points would be assigned. And then you say fit. Okay, so let's run this. You fit the input data, and then you see which neighbors are assigned to it. Okay, so it's almost similar to the previous one. It's just that instead of zeros here, it's all ones. All ones here are zeros, except few, I guess, and then twos. Okay, so what it did is just based on this x parameter, which is your separate length width, pattern length width, it clustered your data and assigned neighbors to it which cluster it belongs to. So it created 3 groups because I asked them to create 3 clusters. Okay, and you could visualize the actual coordinates of this cluster. So if you input k-means dot cluster centers, it will give you the coordinate of the cluster centers. Okay, so what is the coordinate of your cluster center? These are the 4 points or 4 parameters for each. So your x had 4 parameters, right? 1, 2, 3, 4. Separate length, separate width, pattern length, pattern width. So these 4 dimensions. So it's a 4-dimensional space. So you get the cluster centers, you get the cluster assignments to each data point, and it's as simple as that. Create the instance of the class, fit the model. Okay, so how to use it is very straightforward, as it's in all other cases in machine learning we have seen. You create the instance of the class, you pass the parameters specific to that machine learning algorithm, then you fit your model. Okay, questions here in the code? Now here if you see max iteration is 300, it is default value. You can set your number of max iteration also. By default there are 300 iterations and then stop either if 300 iterations have reached. Let's visualize what's doing. Okay, so let's create 3 colors, red, blue, green. What we are doing is we are assigning colors to the group names. So we are saying okay, 0 is red, 1 is blue and 2 is green. And also we are assigning existing neighbors the colors. Okay, so now let's plot. So you see this was the scatter plot before, right, of pattern length and pattern width, which is second and third actually. So you see second is pattern length and third, so 0, 1, 2. So this is what we plotted with the corresponding group which it belongs to. So this is the, after clustering, this is what they have done. So this is all belongs to one group, this is one group, this is another group. And if you see the existing actual mapping, this is the actual grouping which was there. Okay, so let's see it side by side, and maybe it will be more clear. Yeah, so this is the grouping we got from k-mean clustering, and this is the actual grouping. So you see it's almost did the same. So this was one group, so this is perfectly done by k-mean clustering. These were one group, and this is same done by k-mean clustering. There's some mismatch, so if you see the accuracy it will be not. So these are the points where it's making some mistakes. Like in existing one, this one was belongs to red group, but here it's not the blue group but the green group. So these are errors in the machine learning model. So is it clear? So what we saw here is we use that data to do clustering in three groups, and we check okay how it did based on the actual grouping which was there, and it seems to be doing very good now because the error is not much. It's just few points, like 2, 3, 4, 5, like 5 or 6 points which had error. Almost everything else is good. And all these errors are also extreme cases. Like this one, though it is so close to the green points, it's actually red in existing. So it's a special case of this species, which though has the similar. Which one, Sanjeev? So this is a plot of sepal length and sepal width, and the groups. That okay, if this is the sepal length and this is the sepal width, what was the species? So there are three species in this iris data set. Okay, which we call it 0, 1, 2. Suppose we don't know the names. There are three groups. So if this is the sepal length and this is the sepal width, this is belongs to this species or this group. This is the actual mapping. Okay, so some botanist gave this data. Okay, if this is the sepal length, sepal width, this is the species. If this is sepal length, sepal width, this is the species. So there is one species of the kind of red which has this sepal length and sepal width. Okay, but still it's in group 2. So this is your existing grouping of the iris dataset. Yes, that's what we. So we already had this data. Here you see. So this is the flower based on this pattern and pattern width, sepal and sepal width. What was the species of the flower? Okay. In the supervised learning model, we built a machine learning model which, given these four parameters, could predict what is the species by learning from this whole data set, right? What we did now is, okay, we dropped this column, set of this species column. We use on it this data. Okay, if you see just X, we just use X. Color assignment is here. Color doesn't mean anything. It just means there are three groups. So all this belongs to one group, all this belongs to one group, all this belongs to one group. So red here doesn't mean red here. So this is not, it's just that this is one group. Because when you do unsupervised learning, you don't know the name of the groups. You just know if it is same group or different group. Like this point is in group 2 or group 1. So even if you see here, when we did k-mean clustering, these all are assigned a group called group 1, which in actually was 0. But it doesn't mean anything. Okay, 0 and 1 doesn't have any meaning. It just means an ID of the group. Right? Okay, all this belongs to the same group. All this belongs to the same group. Assigning color to the group, we did it here. It's straightforward. So we created three colors called red, blue, green, and for each neighbor we assigned, okay, so 0 is red, 1 is blue, 2 is green. So when you do k-mean clustering, it's unsupervised learning. So you don't know, okay, if this is Setosa or Sentosa or something else. You just know this is one group. Just for visualization, I'm using the colors, okay, because I cannot note 0, 0, 0 and 1, 1, 1 here, right? Is it clear to others? Which is a larger group? What do you mean by larger group? I don't know. So you could count for each group how many elements is in that cluster. Looks like an existing one, green one is larger group. Why that will be asked? Because what is the question you are answering here? So there are two questions you are trying to answer here. First, given these data sets, okay, these points, you were asked, okay, group them into three groups. Somebody knew, okay, suppose this column has been dropped, but they knew, okay, they are from three species. They will say, okay, just consider them into three groups. Okay, then what they will ask you, okay, this data point belongs to which group? This data point belongs to which group? That's what they will ask. That's the question you have to answer. Or suppose a new entry comes, which group it would belongs to? And we do use this also in, suppose, one of the examples we saw last week also was news forums. So you have lots of news articles and Google News is showing it in summary forms, right? So how they do it? So they do clusterings. They try to cluster into groups. Let's see another example. Okay. So this was easier. So there were only 4 dimensions. Let's take wine dataset. So we have our wine dataset. Okay. Where they have like 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, around 12 dimensions. And then there is a category of wine. Okay. It's which group of wine 1, 2, or 3. Okay. So we saw there are 3 categories of this wine. We don't know exactly what is the name of this category. Okay, so we just got it. Okay, they belong to 3 different groups, group 1, 2, and 3. So we'll drop the existing neighbor. Okay, so this is what you will get. And then I will ask you, okay, how many groups are there? How many? So this is what you will get in a k-mean clustering, this input data set, where you have all the properties of the dimension and you are asked, okay, how many, group them into k groups. So if you already know k, then it's easy. You just apply k-mean clustering. Or you don't know how many groups are there, then you have to try different group numbers and then come up with, okay, this looks like a good mix. You got the question?
Yeah, Rohit, actually, what I'm trying to understand here is this is categorization is possible to uh, view it only using the graphical presentation, or it can also be possible through the numbers?
Numbers is there, right? So graph is just for visualization. So otherwise, when you see k-means.neighbors, it gives you for each input point what group it belongs to. For each input row, it knows okay what was the neighbors.
Okay.
Like we will see here in the wind dataset, because there are so many dimensions, we will not be able to visualize it. What we know at the end is okay, just the neighbors. Okay, each point is, so this is which category. So this is group 1 or 2 or 3. So it will actually just group it.
Okay.
So visualization is not something you have to always do. It's just to show you that okay, it makes sense that why it grouped it like this. But what you get is this. So you fit the model, which is your x dimension, these values, and then for each individual value, like this is the first row, right? Where your pattern length is this, width is this, upper length is this, width is this. The neighbor is 1. For the second row, neighbor is 1. For third row, neighbor is 1. For some other row, neighbor is 0. I don't know, this is like 30th or 31st. For this row, the neighbor is 2. Is it clear now? So now we are doing same thing. So this is what you get. So this is your input data. So you have row 0, which is for each dimension or each feature you have the values, and you have to assign a group to here. We already had this assignment, but we have dropped it because it's unsupervised learning, and we do it ourselves. We try to group these vines into different groups. Okay. So is the question clear what we do in unsupervised learning? That okay, you get the feature vector, and you have to specify the neighbor, which class it belongs to. So first thing you have to do, okay, how many classes are there? So suppose you knew that okay, there are 3 classes, then you just apply k-mean clustering saying number of cluster is 3, as we did here. So you will say okay, k-mean cluster, number of cluster is 3, fit the model. It will then use all the data you have and then cluster it. Okay. Now the important question is okay, how you, so if you already knew k, then it's okay, but what if you don't know k, that you don't know how many groups are there? So what you can do, one approach is okay, you try different values of k and then see how the clustering is happening, and then go to each cluster and see if it makes sense, either by visual representation. Like in this case, you see okay, does it make sense? If 3 groups are okay, you try 4 or 5, and because you don't know actual number of groups, there is no right answer. So as long as it makes sense, so we'll see this example in text clustering, that what it means by makes sense. But there are some statistical approaches also to get the optimal number of clusters. Okay, so one approach is called the elbow method. It's quite popular. So what elbow method does, it looks at the percentage of variance explained as a function of number of cluster. So if you remember, we discussed what is variance. So just think how much of the data could be explained using the number of clusters. So you see, okay, how much variance is explained using cluster number. If the number of clusters are 2, how much variance is explained if the number of clusters are 3. Okay, and then you choose a number of clusters so that adding a new cluster does not give much better increase in the percentage of variance. So let's take this an example. So suppose you have this wine data set. Okay, so the original wine data set. So wine df, okay, not the wine features df, just wine df. You take the x coordinates like these elements, the y is your label, the initial label. You need only x, so you do for I in range 1 to 11. These are your number of cluster, cluster 1, cluster 2, cluster 11. You do k-mean clustering. Okay, and then when you do a k-mean clustering, it also gives you inertia. Okay, what is inertia? Inertia is your within cluster the sum of square error. Okay, and then you plot this. So it's an indication of your variance in the data. So what you get, okay, when the number of cluster is this, the within cluster sum of squares is around 1.75. When number of clusters is 2, is 0.5. So you see, when you increase from 1 to 2, the change in variation is very high, right? When you go for 2 to 3, again there is a change in variation. Then you go to 3 to 4, there is small change in variation. 4 to 5 is very small. 5 to 6 is even smaller. 6 onward, it's almost negligible. So you see the change in variance. So this is your variance. So the measure of variance we are using here is in within cluster sum of squares. Okay, so this is one parameter which you get from something on inertia. Okay, so you plot this and you find out, okay, which point gives the least variance, uh, after which point the decrease in variance is minimum. Okay, so that's why it's called elbow method, because it looks always like an elbow. So after some point the decrease will be very low. So that point is a good approximation of your number of clusters. So here you see after 3 or 6, so I think now 6 would be a good number of clusters, because this after this the variance increase is very low. Even 3 is good, I think. So now this is more subjective. You could use 3, 4, 5, 6, any one of them. Okay, at how much decrease in variance you think is negligible. You could actually see the values itself. So here we plotted all these value from k is equal to this number of clusters from 1 to 11. You could view, so here I'm just printing them. So k-mean cluster for number of cluster as 1. This is the value, this is this value, this is this value, this is for I think 4, this is for 5. Okay, so you can actually view the numbers also, but generally you plot them, because then it gives you a feel, okay, where the bending has become slow. So after 3 or 4 it is very low. So from this you think, okay, let's use first 3. Okay, so you decided, okay, 3 is a good point, after which you see the elbow is bending, right? So this is where you think is a good bend. So you can take 3 as your number of clusters. So does this make sense, this elbow method? These are all subjective a bit. Okay, so there's no right answer, because nobody knew how many groups are there. So this gives an indication, okay, how many groups, because so if you add more group, you see there's not much difference happening. So in this, so that's and again some equation. Okay, so this is inertia, which is your within cluster sum of square. So when the cluster is formed, each point in that cluster, what is the sum of square distances? That is what is variance here. So you can directly get it with something called k means dot inertia. WCSS is the short form of this, within cluster sum of squares. WCSS. That's the short form of full form of WCSS. Within cluster sum of squares. So you had, suppose this is the cluster, right? So within this cluster, what is the square distance of this on the within sum of distance square sum of distances. Sorry, within cluster sum of squares. In this cluster, it's holding an array. No, it's just one value for each cluster. What is the sum of squares? Sum of squares. Sum of squares. Within cluster sum of squares. See, it gives one value. So you can find this cluster square, this cluster sum square, this, and then sum them up. It's kind of a degree of how much they are far from each other and how much they are close in within a cluster. Okay, so suppose we take from this visualization that cluster k is 3, then it's simple, right? So you say k mean cluster, number of clusters is 3. Okay, you create 3 clusters colors, you fit your model, then you visualize the colors. So okay, now the visualization is not possible here. Why? Because you don't know which specific feature you should project it into, because there are two, and so here we just use 2 features, right? Feature second, third and fourth. So there were 4 features and you projected on these 2 features, and it was kind of giving good visualization. Now here in case of wine, there are so many features, so it would be like 2n dimensional space. So there's no way you can visualize a 2n dimensional space, right, in a graph. It will not make much sense. Actually, when you visualize it in 2n dimensional space, you could see the clusters more nicely, but obviously that's not possible. So that's why there's this element which we'll see now is called principal. So you understood the problem first, right? What was the problem? So clustering, there is no problem. So it clustered. Now, but when we wanted to visualize, we don't know how to visualize it because there are so many different dimensions. We don't know on which dimension we should project and visualize so that it makes sense, because there are 12 dimensions, right? So what we use is something called PCA, principal component analysis. Okay, what is PCA? It's a dimensionality reduction algorithm. Okay, so does this term make sense, Sonia? So people actually who is from data warehouse background, they would have heard of this term, dimensionally, so you reduce the number of dimensions. Okay, I don't know if Sonia is also there. Sonia, you understood the question? Yeah. So you have any example of where you do dimensionality reduction in real life? So have you ever done this reducing number of dimensions? Sanjeev or Sonia, anyone? Not in work. Apart from work, have you ever done this? Reducing number of dimensions? I think all of you would have done dimensionality reduction in class 5 or 6. I did it when I was in class 2 only. So what do you mean by reducing number of dimensions? So suppose here in wine dataset we have 12 dimensions, right? And what I want to do is reduce into 2 dimensions only. Okay. So when you go from 3 dimensions to 2 dimensions, everybody would have done it. So if somebody asks you in school, okay, draw a cat or draw a bat, okay, draw a bottle, suppose. Okay, my drawing is very bad. I will try. So if I ask you to draw a bottle, you do something like this, right? Like, okay, I don't know. So this is how you draw a bottle, right? Okay. So this went too far. It's not, maybe not this. Suppose this is a crude example of a bottle. Now a bottle in real life is 3-dimensional, right? But when I ask you to draw it, you could draw it only in 2 dimensions, right? So this is a 2-dimensional picture of a 3-dimensional object. And everybody had do it in school, right? Now why I draw that bottle? So when you see this, could you recognize this is a bottle? Somehow, okay, it's not a very good example, diagram. But still, right? So this is what dimensional reduction is. So you had a 3-dimensional object in a bottle in 3-dimensional space, right? It's 3D. And you projected it into a 2-dimensional space. And this is your projection. So you reduce the dimensions from 3 to 2. Now you could have drawn a bottle like this also. Okay, and I will say, okay, this is also a bottle from top view. So if you view the bottle from top, this is how the bottle suppose looks like. And this is how the bottle looks like when you're viewing it from the side. So both is actually a projection of the 3D object, a 3D figure into a 2D dimension. Now out of these two, which one is better? This one or this one? This is suppose 1 and this is 2. Which one you think is a better projection? This one, 1 or 2? 1, right? So though both are correct projections, this one is a better projection. What PCA does for you, using lots of complex mathematics, which I don't want to get into, is exactly the same. Okay, so it finds out the axis and the projection, which gives you the best picture of that reduced dimension. So it explains maximum variance in some way. Like it explains a lots of about the reduced dimension. This is so without going into mathematics, because there's too much mathematics on that. What PCA would do is, if you ask PC to draw a bottle which is in 3D to a 2D, it will draw it like this instead of like this, based on the mathematics it has inside it. Okay, so is it clear now what dimensionality reduction means? This was a simple example of from 3D to 2D. Okay, but we are doing with a vector space of n dimensions, so you can actually reduce from n dimensions to k dimension, where k is less than n. Okay, so you could go from 12 dimension in this case of wine to 3 or 4 dimensions. Okay, and then it will find out the values corresponding to each row on those axis dimensions, right? So now these are also, so you had these points in 3D space. Now each point, how now it looks like in a 2D space. So this is what PCA would do for you. And why it is used, it helps you to visualize the result in the now in the reduced number of variables and reduced number of dimensions. Okay, is the concept clear, Sonia? Good. So how it works, so again you import, so there's this library called sknn.decomposition. It has this class called PCA. So when you create PCA instance, you say okay, PCA number of components. So how many variables were there, you don't care. You say okay, reduce into two variables or 2 dimensions, or reduce it into 3 dimensions. Okay, then similar to k-mean clustering, it also has, so you fit the model, your data set, you give the data set to it, and then you check okay, what is the explain PCA is used for dimensionality reduction. So you, instead of using 12 variables, you want to use convert them into 2 variables. So earlier what we saw was feature extraction, right? That okay, drop some of the features because it doesn't make sense. But in k-mean clustering, which is unsupervised learning, you don't know which feature does not make sense, right? Because in supervised learning, you could do a coordination between the target value and the variables, and then see okay, these does not make sense, so you could drop one of them. But in unsupervised learning, you don't know which dimension to drop, or which variable or which feature to drop. Okay, so what you could do is you could do feature reduction by combining these features as one feature or 2 features. So it will create, combine these values and create a new feature for you. Okay, so it's actually creating new features for you using the existing features by doing a projection. So it's actually projecting from this 2 dimensional space to k dimensional space, where you specify how many features you want. How it does that projection, I don't want to get into. So just think of it as okay, earlier it was in 2 dimensions, same as the example we saw here, right? Okay, earlier you had a bottle in 3D. I said okay, no, I didn't only in 2D, give me a 2D image of this bottle. So PCA will give you this image instead of this image, because both are correct representations, but this is a better representation, right? So there would be 100 bottles, each would be, or 100 objects in 3D, which would be reduced to two-dimensional objects, and then it would be classified using only these two-dimensional pictures. Okay. So here what we did, so how PCA works internally is that, okay, the first dimension which it projects to have the maximum variance, the second would be a bit more than that. So if you just take two, it's by taking two dimension, it explains around 99.98% of your data set using just two these features. If you convert these 12 features into three features, it explains around 99.99% of your data. If you convert it into four features, it explains around 99.997, like a bit more. But even two features is around good enough. 99.98% of your data is explained using just these two reduced features. Okay, from 12 features, you reduced it into two features. Not by dropping something, but just combining them from 12-dimensional space to a two-dimensional space. Okay, so if you see the values earlier, where's my wine data? So earlier, this is your input row, right? It has 12 values: 14.23, 1.71, 2.43, and now this has changed to this 3.1856, 2.149 into, yes, is 21.4, 318.56. These two values. Now what these values are, these features doesn't have any meaning. Okay, because it's a projection of those 12 features. Okay, so I cannot specify a name to these features, but it's just a projection. Okay, Sonia, is it clear? If questions, just ask. No? This is a bit complicated topic, so if it's not clear, I can understand, because it's the first time I'm asking you to think in 12 dimensions. So we are used to thinking in 2 and 3 dimensions. That's why I took this example of bottle. But not think if there are 12 dimensions, and that has been reduced into 2 dimensions. Okay. Yeah. Number of components you got to 2 is saying keep 2 dimensions. Like create 2 dimensions, not keep actually. Yes. It's just let me finish this, and then we'll take a break. Okay. So now what we did, we divided into 2 dimensions. So this is the code for that. So you create an instance of the object PCA. You do fit transform of your features data. So now your feature data is transformed using PCA into 2 dimensions. You can see the values. Okay. Now, because it is 2 dimension, you can visualize it. So now, if you remember, we divided into 3 clusters, and this is the visualization of these 3 clusters. And now it looks also okay. This is on one group, this is one group, this is one group. So it's a good grouping. Okay. And now this is the existing layout. of the wine data. This is what we got from k-mean clustering. So now we are able to visualize because we reduced into 2 dimensions. Okay. Now here is the same example with 6 clusters. Again, difference between k-mean vision where this is not clustering. Okay, okay. Here what I'm visualizing is the actual data, because for each wine we had their actual mapping also, right? In the actual data set. Okay, that this is wine 1, this is wine 1. So this representation is what was the actual grouping, and this is what we got when we didn't knew the grouping and we did into 3 groups, right? So I'm just checking how good it is map. So this is just to validate, okay, the grouping we did, how good it is to the existing one. So we saw that, okay, there are some parts which are wrongly grouped, but okay, it's a machine learning model, there are some errors. Yes, it's not improvement, it's like good grouping, but there's because it's not improving, because this is the actual grouping. So if you're able to group it exactly like this, then it's a very good mapping, but it will be an overfitting somewhat. Okay, so this is your actual grouping. This is from the, without knowing the groups, just using the data you did a grouping, and this is what you got, and then you saw, okay, it's not bad. Okay, so I think it's a good time to take break, and then we'll go to another clustering algorithm called hierarchical clustering. Okay, what's the time now? So let's meet at 11:40. Okay, Sonia. Hi guys, please message if you're back. So Sanjeev, any questions? Let's wait 1 more minute and we'll start. So up till week 14, the presentation has been updated, and this presentation will be updated next by Tuesday. Okay, let's start. So we saw key mean clustering. Now there's another approach of clustering. It's called hierarchical clustering. Hi Sony, right on time. Huh? We're just starting. So, any question on K-mean clustering? Is it clear? So we saw K-mean clustering and we saw PCA, principal component analysis, which is used for reducing number of dimensions. Okay. Now we are seeing a new approach of clustering. It's called hierarchical clustering. Okay. So it has two parts. Like one is called bottom-up approach, another is called top-down approach. Okay. So the bottom approach is called agglomerative, and the top-down approach is called divisive. Okay. And as the name suggests, it's very easy to understand. So the bottom-up approach is what? Each observation, so each data points, like in this case, so suppose this is my case, you will say, okay, each data point is in one cluster. Okay, that's how bottom-up approach works. So each data point itself will be one cluster. So each observation starts with its own cluster, and then pairs of clusters are merged as you move upward in the hierarchy. Okay, so you create a new cluster by merging existing two clusters. Okay, and divisive is the top down approach, which is exactly the opposite. You assume everything is belongs to one cluster, and then you divide this one cluster into two clusters by splitting them, and then again you split. So this is how the divisive or the top down approach works. Okay, so we'll see an example using, so for top down approach, and it's a bottom up approach, and it works similarly for the top down approach. Okay, so the three important things which has to be considered for hierarchical clustering is that how you represent a cluster. Okay, that what you mean by when you say, okay, it's a cluster. Now in case of Euclidean space, the center of the cluster represents a cluster, right? So we call it centroid. But in hierarchical clustering, you could also do non-Euclidean space clustering. Okay, and in that case, it is called clusteroid. But all these terms, if you don't understand, is okay. But the main thing is how you represent a cluster. Then how you find the distance between clusters. Okay, and then next step is when to stop. Because, so let's see an example. It works both for Euclidean and non-Euclidean space. So suppose you have these 5 points or 5 data points A, B, C, D, E, F. Okay, and you want to cluster them. So you are already given your measure of what is a cluster center or what is a distance, is how a distance is calculated. All this is given. Okay, so based on that, what it does is it says, okay, A and B is more close and D and E are more close. Okay, so you see A and B are more close and D and E are more close. So earlier all of them were in single clusters. In the second step, it will merge A and B together and form a new cluster. D and E would be merged and it will form a new cluster based on the similarity, how close they are. Okay. Then in second step, A, B and C are now more closer. So it will be merged together. So this is one cluster, two cluster, three clusters. So these are three clusters now. Next step, F would be merged to D. So you have one cluster, two clusters. And finally, these two would be merged to form one cluster. So everything is one cluster. Okay. Now you have to decide when to stop. So if you turn the algorithm that stop when the number of clusters are 2, then it will stop here and it will give you output as, okay, this is one cluster, this is one cluster. If you turn the algorithm to stop when the number of clusters are 3, it will stop here and it will give you output as, okay, this is one cluster, this is one cluster, this is one cluster. Okay, if you would have told it, okay, the number of clusters are 4, it will stop here and it will give you output as this, this and this. Okay. So this thing which we get here, this is called a dendrogram. Okay, it's just a hierarchy of the clusters, that how the cluster was formed. So this is the extra information which is given in this algorithm, hierarchical clustering algorithm, which is very useful. Okay, so let's see it in practice. So you could directly create a dendrogram using this package in clustering called hierarchy. Okay, so what you said, okay, and this is called linkage. Okay, so you say create a dendrogram, and you can visualize the dendrogram using this code. So you say, okay, create a dendrogram by linking from this data wine data feature, and method we use is word. So word is one of the methods which is used to find the distances. So it actually minimizes the variance in each cluster. Again, this is used for Euclidean distances. So if you visualize, this is how the clustering is done. So it merges each data points put into one cluster. So till now it's one cluster, second cluster, third, and then it's merged into one cluster. So you could stop at this point when there are four clusters, or you could stop here and where there are one, two, and three clusters. Okay, but you get the good output from this. So this is not a very good example. So I was thinking of adding a new example. I couldn't find it because hierarchy is very useful in some cases. So we put a new example for hierarchical clustering. Maybe wine dataset is not the best example for this. Okay, so just see the code first, that how we do it uh, using the machine learning code. So in sklearn cluster, there is an algorithm called algorithmic clustering. So it's again like k-mean clustering. You say, okay, how many clusters you want, and what is the linkage method to use. So by default it's word, so you don't have to specify your also. So by default it will use word method. You create a instance of this class, and then you said, okay, fit the data set. Okay, and then if you visualize it, it's also doing the same clustering. So the output is almost similar to k-mean clustering, because it's also doing the clustering of data. The difference is this is using a hierarchical approach. So it gives you this dendrogram. It creates a dendrogram like this. So the approach of clustering is different. That's the main point. Like both of the algorithm, k-mean and hierarchical clustering, do the same thing. Just that approach of how it does the clustering is different. Okay. Questions? So this is the last algorithm we'll see. So we are finishing unsupervised learning. Now we are moving to something else. But before that, I just want to say, okay, if you have any questions on supervised learning algorithms or unsupervised learning algorithms. So we saw like around 4 or 5 supervised learning algorithms and around 2 unsupervised learning algorithms, the clustering algorithms. Okay, split example. Top-down approach, you mean? So this was bottom-up approach. Yeah, right now I don't have an example. We could use So there's an algorithm called decisive clustering. Okay, but again, it will give the same output. So actually, I need to find an use case where the dendrogram makes sense. Okay, so example, suppose, so it's like, okay, you're clustering animals. No, not yet. Running was just exactly the same. So it will run just opposite. So it will start like this. So just look into the reverse. So how top-down approach will work? It will put everything in one cluster, and then it will split here, saying, okay, this is one cluster, this is one cluster. So this dendrogram will be created in opposite direction. So the top-down approach is just reverse. So instead of coming like this, you think go like this. Okay. So now we are coming to a very important topic called cross validation. Okay. So another recap. If you remember when we are doing this machine learning algorithms for supervised learning, we used to split the training, our data set into two parts, right? Train and test split. And we are creating an X data set and a Y data set. We have to specify how much we want to put in a training set, like 75 into training set, 25 into test set, and we will give, okay, random state is 0 or anything random state, and then you find the prediction, right? You remember this step? So this is, I think, logistic regression. Now what if I just change this from 25 to suppose 30? So now it is 96.79%. I have to run the whole thing. So I think I have an example here also. Yeah, so this is my Titanic data set. Okay, this was my Titanic data set. I created X and Y. So X is on these values, Y is the survived yes or no. Then I'm splitting into training and test, creating a standard scaler, like we am standardizing. So this step you remember, right? The normalization of the vectors. And then I'm doing logistic regression. So let's run this, and I'm getting an accuracy of 82.0627, 82.06. So this was logistic regression which we saw last time, right? So what does accuracy tells me? That okay, it's around 82% accurate. But let me just change this random state to something else. See, the accuracies have changed from 82 to 81.6. Like if I don't give it a random state, so every time I run it will give me different accuracy. Can you see this? 79, 80, 81, 81, 82, 78, 74. Now which accuracy is correct? First of all, why it's giving me different accuracies? My data is same, my logistic regression model is same. So why you think it's giving me different accuracies? Okay, what is random? So what is the random part in this whole so if you see this, what we are doing here, training and test split. So this data, I'm randomly picking one row as a training set and another row as a test set, right? So I'm randomly picking 75% of the rows as a training set and 25% of my rows as a testing set, right? So my training data is changing, my testing data is changing, and that's why my accuracy is changing. So is that clear? So that's the problem. The results or the accuracy will not may vary. It almost every time varies depending on the way. What is vectorization? Vectorization is just converting your features into one vector. So we represent our features, like which are these columns here, as a vector. When we talk about this dimensions, dimension space. So if this is my 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. This is your class table. So 9 dimensions. So a vector in this dimension space with these values represents this feature vector. Okay. But is the problem clear? So what was the problem? The result and accuracy may vary depending on the way the training and test set are divided. Now what is the solution to that problem? That ensure that every sample from the original data set has the same chance of appearing in the training and testing set. That's an easy forward solution. Right? Okay, we make sure that all the data, all the examples in the training data in the original data set appears in the training and testing data set. And then we evaluate the model in practice and ensure that it is correctly trained without picking up too much noise. But this is possible only in practice. But what we do while training? So the achieving the solution while training, this approach or this method is called cross validation, where you make sure that every example from the original data set has the same chance of appearing in the training and testing set. So what does cross validation does? It defines a data set to test the model in training phase called validation set, and then perform multiple rounds of cross validation to reduce. So in simple words, what it does it. So what I'm doing here, it will rerun this whole thing multiple times, ensuring that every time all the values goes into training set and some of the values goes into test set, and then find out the average accuracy. Okay, so there are different approaches of cross validation. So let's take the first one, which is the most famous one, which is called k-phone cross validation. Okay, so how does k-phone cross validation works? It divides the samples or your input data into k groups. So suppose let's take an example. So suppose you had 1,000 rows here. Okay, in your there is my data set. So suppose this is my data set and there are 1,000 rows in this. So it will divide it into, suppose I said 10-fold cross validation. So it will divide it into 10 parts. So each part will have 100 rows in it. Okay. So it will be 10 cross 100 samples. So divide the samples into k groups. These are called phones. Now the prediction is done. So let's visualize it like this. 3, 4, 5, 6, 7, 8, 9, 10. Suppose these are my 10 groups. Okay, group 1, 2, 3. So I set 10 fold. So it divided, each group will have how many rows? 100 rows. Okay, so 100 rows in each elements in each group. Now this grouping is done randomly. So every sample is in one group and it is randomly put, and there are 10 groups. What it will do, it will first pick 9 such groups. Okay, call it a training set, and this will become your testing set. Okay, so your training set is 1 to 9 and your testing set is 10th. Okay, now it will, on this training set, it will do the logistic regression learning, and it will test on this last sample. Again, it will repeat it 10 times. So next time it will create a training set from 1 to 8 and 10, and your testing set would be 9. Okay, so your, this becomes your testing set, and this becomes your, and this will keep on repeating. So now it will be 1 to 7, 9 and 10, and your training set would be 8. So what's happening now is each sample gets equal number of times to be in the training set and equal number of times in the testing set. And then in these 10 runs, it will find the accuracy, and then the average accuracy would be the average of that 10 accuracies. Do you understand how it works now? It's very simple. So this is called k-fold cross validation, like dividing the sample into k groups and then predictions in k minus 1 folds while leaving one out, and then repeat it k times. Easy. Like when I first read it, I thought, okay, this makes sense. And like if I didn't knew about k-fold cross validation and somebody told me, okay, this was the issue, I would also have done something similar. So this very intuitive way, it's very logical way of finding the accuracy, correct accuracy of your model or validating your model. Okay. So this is also used to compare different machine learning models. So suppose you have 4 different models. Okay, Sonia. No problem. Bye. So it's me and Sanjeev on it. One and only class for you, Sanjeev. So is it clear now? Now there are different variations to this. Okay, so you can repeat k4 n times. So what it does, the groups which are created will be created n different times and then repeat the same thing. And it is used for comparing with different models. So you could have 2 different machine learning models, like using logistic regression and one with using random forest. Then you find the average accuracy using k4 cross validation, and then you see, okay, which one has an on average highest accuracy. Okay, there's another one called naive one out. Okay, in naive one out, instead of creating k samples, what it does, it uses on your input data as your training set and only one as your testing set. Okay, so in this row, suppose there are 1000 rows, it will use 999 rows as your training set and one row as your testing set, and then it will repeat, so that, okay, each time you get only one row as the output set, as a testing set. So this takes more time. Now there's another one called random permutation cross validation. What this one does, it, instead of creating k samples which is consistent at the same time, every time it will every time you run it. So if you tell it, okay, create 10 groups, so it will randomly create 10 pairs of training and test sets, and then test on those 10 randomly created training and test sets. Okay, it's like running this 10 times and taking the average of 10 runs. Okay, so the difference between the three approaches is clear. K-fold, leave one out, and random permutation cross validation. Perfect. Now there's uh, extra version of it, or extended version of it. It's called cross validation with stratification based on classes. So what does stratified k-fold means is that when creating the folds, okay, when the variation of these k-folds are created, each sets contain approximately the same percentages of sample of each H target class as the complete set. What does this mean? That okay, if my target set is where's my data? So here it was only 0 and 1, right? Like okay, survived yes or no. But you could have, your class could be, I don't know, you have 10 different classes out of which you have to do the predictions. So the samples which are created is such that each sample has approximately same number of representation from each class. Okay, so if there are 10 classes, each sample will have like 10% of each class. It cannot guarantee exactly same because the data has to be like that, but it will try to give equal uh, percentage or same percentage of the samples of each target class in each sample, each fold which is created, each this sub parts which are created. So this will have, in case of binary, it will have like 50 survived, 50 dead. This will also have 50 survived, 50 dead. This will also have 50 survived, 50 dead. If there were three classes, this will have like 33, 33, 34, 33, 33, 34. So these are equal uh, percentage. Exactly equal. It will try to have equal distribution of these classes. Okay. So let's see some examples. How the number of classes identified? It's supervised learning. So you will have the number of classes in your train. So here it's only two because it's 0 and 1. I think there was cases. So in iris dataset, the number of classes were 3. So there are 3. So you know the number of classes based on the target, the unique value of target values. That's your unique number of classes. So these are the same terms, huh? Target values, classes. Yes, because you have to train and test, right? So unsupervised learning, there is no testing as such. You just find clusters. So the problem of training and test division was only in supervised learning. Okay, so let's see how it works. So all these things which I talk about, that okay, dividing it into different groups, then cross-validating, then finding this average score and all these things could be done just using one line of the code. So there is a method called cross-validation score. Okay, so you create your model. So you say I'm using a logistic regression model. So you create an instance of the class logistic regression. You pass some parameters you want to pass to it. You pass your complete data set X, your prediction Y. You say, okay, give me 10 folds. Do a 10-fold cross validations. Now, how many fold you should do? In industry, people usually do 10 fold. So 10 fold is very popular. So you could do 3 fold, you could do 5 fold, you could do 7 fold. But 10 is quite popular. Okay, so 10 fold cross validation. And you run this, and it gives you for each fold what was the accuracy. And then you can also get what was the mean accuracy, what was the minimum accuracy, what was the maximum accuracy. Okay, so using it is very simple. So you don't have to do it yourself. You don't have to run it 10 times, 20 times. It will do it automatically for you. So what this line of code is doing, it's running the cross validation for this logistic regression model. You could pass any model here. Okay, so I'm passing a logistic regression instance. I'm passing my training set. I'm passing my testing set. Not testing, sorry. I'm passing my features. I'm passing my classes, and then I'm seeing how many folds it has to do. Okay. Now this is the example of random sufficient split. So there's a method called yes, because you could do cross validation for any machine learning model, right? Supervised. So in the examples here, I'm using logistic regression, but you could use random forest or you could use naive Bayes. So the other approach which we saw, the so let's take an example of stratified Ceph split. So there is a class called stratified Ceph split. Just create an instance of you say how many splits you want. So you say 10 splits, so it will randomly, and the test size is 0.2, right? So what it will do, it will create 10 random samples of training and testing data with training as 80% and testing as 20% of your data. So this is actually an array. That's why you iterate over it. For each sample of training and test, then you run your logistic regression and you get the accuracy. Okay, and you could take a mean of this. So one good exercise at home would be try to implement cross validation score function yourself and not for a generic machine learning method, for suppose logistic regression method. Okay, so for logistic regression method, try to implement cross validation score as a Python function. That's a very good exercise. So is the concept of cross validation now clear? Good. So now we are moving to another concept called grid search. Okay. So the problem now is, okay, you have 10 different models and you want to find the best model, right? One way you do cross validation approach on 10 different models yourself, okay, and then pick the best model, seeing which one gives the best accuracy. Or you can use something called grid search. Okay. Now here by model I mean, okay, if you remember, I don't know, random forest. We had example of random forest here, right? So this is your random forest model, right? It takes something called number of estimators as a parameter, right? So there are some parameters, and based on that parameter, it does some predictions, right? You remember random forest? So what was number of estimators in random forest? It was the number of features it should use to do the classification. And it chooses top 5 features or top 7 features or top 8 features, right? So the same model, depending on how many features you select or number of estimators you select, could give you different accuracy scores, right? And all these models are actually different models, right? Because one model is trained using 5 estimator, one model is using 6 estimator, one is using 20 estimators. Then how we know which parameter settings gives you the best result? Now you could try it yourself for each different parameter settings, find the accuracy and then pick one which gives the best. Or you could use something called grid search. What grid search does is that it automatically runs on these different permutation combination which you specified to, and then give you the best parameter setting for which it found the best results. Okay. Now there's one very good example to show the advantage of grid search is digit recognition. Okay, so there is a data set in sknun called digits. So we could node it using node digits. So this is what looks like. Okay. So your training set has digits, pixels like this, and it is mapped. Okay, this picture is 0, this is 1, this is 2, this is 3, and then given a new image, you have to predict whether it is 8 or 4 or 9. Okay, so this data set is available in sknun. So what we are doing here is we are training a support vector machine. Okay, so support vector machines are very good in your digit recognition kind of problems, and it has multiple parameters. So we're not going to details of these parameters. Okay, so there's a parameter called cs, there is a parameter called gammas. Okay, so you could, and then there's a parameter called kernel also, which kernel you want to use and all those things. So you can run this model, it will do. Now what happened here, let's see. So you could run svc with any one of these parameters, like okay, cs is 1 and gamma is suppose 0.1, or cs is 1 and gamma is 0.01 on this different combinations. Now by passing it as a grid search cv, you said okay, this machine learning model, run it on these parameters, where my cs could take any value from this to this, gammas could take these values. So it will rerun this same algorithm in this different combination of values. Okay, it will fit your training and test your neighbor, your training data, and then it will find out the scores for each combinations, and at the end it can give you the best parameters. So it will give you the best score and best parameters. So in this way it found okay, for c is equal to 10 and gamma is equal to 0.001, you got the best result, that is 96.27% accuracy. So you could have done it yourself with your own hand, that okay, run this with this combination with, so how many combinations are there? I guess 1 2 3 4 5 2 3 4 4 into 4, 16 combinations. So for each combination, these are the 16 accuracy scores, and it picked up the best one for you. Obviously you can do it yourself, but if suppose there are 100 different permutations, then running it yourself 100 times is better to do a grid search. So this is, so there is no special algorithm involved. It's just doing this manual work of rerunning it depending on different parameters for you. There's no maths or no algorithm involved in this in grid search. Okay, what is doing is just running your model on the combination of the parameters which you have provided, and at the end it gives you the best score and the best parameters. Okay, so we think I have another example. Yeah. For the iris data set. Yeah, in this case, C10 and gamma 0.01. For this parameter, the model was the giving best performance. So in the simpler case, like suppose, yeah. So if you see the simple example of random forest classifier, where we have number of estimators as 5, right? So we create different array of number of estimators like okay 5, 10, 20, 50, and 100. Okay, and then we do a grid search. We say okay, in this grid search use cross validation with C4 10-fold cross validation. Use scoring as accuracy. Verbose means how much information you want it to print. Okay, so there are some extra parameters in grid search. So we are going into those parameters. So grid first takes what? Your algorithm, learning model, your list of parameters on which it has to run this model. I am saying CV is equal to 10. So grid search always uses cross validation to find the accuracy. Okay. So I'm saying for cross validation use 10-fold. Scoring I'm using is accuracy. The default is also accuracy. Verbose is how much printing I want. And all this runs could happen in parallel, right? So I say okay, run 4 jobs in parallel. I could. So this is parallelizing each different runs, and then get me the best score and best parameter. So it gave me okay for number of estimators is 10 to get the best prediction. So out of these 5 parameters, 10 gives the best result. Yeah, in this case, it's giving almost 100% accuracy, which could be an over fitting. So now these are again subjective. For CB is equal to 5. So see in cross validation we saw okay it's 1.99, 1.96, 0.966. So average would be 0.967 something. You're saying cross validation is 5. So if you do a cross validation on 5-fold, it says okay 20 is best. Okay. So now we don't have much time on it. Yes. to answer your question now, that okay, which modern is best? So this is the second hurdle. So the first part was, I said you spend 80% of your time in data pre-processing and data cleaning, right? Then training your modern is very fast. It doesn't take much time because there are algorithms given, you run it and done. Then the last 10 to 15% of your time is goes on picking up the best model. Okay, so there are different approaches on how we could evaluate your models. So we'll see some of this, that how you evaluate your models. So cross validation was to get an average accuracy, so that okay, your model is not giving so that everything is compared in the same slate. Because of the randomness, it could be that okay, one model is giving more accuracy because the training set got such data that accuracy improved, right? To avoid that okay, it's not just by chance that random and test net split happen in such a way that one model is giving better result than other. We solve it using cross validation, but even after that, what are different approaches in which you could compare two different models? Okay, so that's what is our next topic, modern evaluation. So you understood what we meant by modern evaluation? What is the thing we want to do? So what is modern evaluation? Not just accuracy, because accuracy is not always good. So just having 100% accuracy doesn't mean this modern is good. So modern could give 100% accuracy, but still is not a good model. Okay, so there are different ways you could compare different models. So we'll see what I mean by that. So for linear regression, we already saw there are two approaches which you use for modern evaluation: the root mean square error and the R squared values. Okay, so there it was straightforward. That okay, how much is the root mean square error? If the value is low, it's a good model, right? Now for classification problems, there are many more approaches. Okay, depending on how you want to evaluate it. So there's confusion matrix, there's F1 score, AOC ROC curve. Okay, then there is something on gain and F chart, KS chart, Gini coefficient, concordant discordant ratios. Okay, so I don't think we'll have time to cover all of them today, so we'll cover some of them today and then the rest of them we'll cover in the next class. Okay, so let's start with confusion matrix. Okay, so what is confusion matrix? So if you remember, we saw this example in last class also. Last to last class, I've actually redoing it here. So we used exactly this same data set, the Titanic data set. So on this steps would be clear. So we did data pre-processing. So from here to here is on data pre-processing. So just to reiterate and summarize what we did in machine learning, like in the whole 3 weeks and just one slide. This is data pre-processing. Like we are filling age values with mean, missing sex values. Okay, we are dropping some features which we know does not make sense. Age with mean, fair with median, because of the distribution of that data. Okay, here we are doing encoding of your data, and then finally we have our prepared data. We divide it into our features and then our labels. We train our model, we split the data into training and test set. We do our feature scaling, and then we do our training. Okay, so any questions here in all of these steps? So this is on this is what we did in week 12, 13, 14, or 11, 12, 13 kind of. Okay, data preparation, data scaling, feature selection, running the logistic model. And then we saw something that okay, there is a function called confusion matrix. So you can pass it your actual labels and your predicted labels, and it gives you a confusion matrix which is in this format. So you have true negative, false negative, true positive. Okay, so you can get these values. What is true positive? When your prediction was positive and the actual result was also positive. Okay, so I'm saying positive negative here because I'm considering a binary classification, right? That okay, so I'm saying a positive cases when the person survived, so that's a positive case for me. And if the person died in this example of Titanic, if the person died, then it's a negative case for me. So if you predicted that he survived and he actually survived, then it's a true positive. So this is used a lot in your drug analytics. Okay, so when a new drug has been discovered or made and they test it on different patients, then they get true predictions. Okay, how many times they actually fixed it and how many times it worked. So what is the two positive cases? So what was false positive? That okay, you found that okay, it is positive, but actually it was negative. So you remember our tumor example, right? You said okay, the tumor is cancerous, but actually the tumor was not cancerous. Then false negative, where you say okay, it was not cancerous, but actually it was cancerous. And true negative, when you said okay, there is no cancer, and you actually there was no cancer. Okay? So from this confusion matrix, you can create multiple things. You can calculate multiple parameters. Suppose accuracy. So what is accuracy? Accuracy is easy. True positive plus true negative divided by total number of case. That is your accuracy. But what is the sensitivity? What is the precision of this model? So you the precision is given by true positive divided by true positive plus false positive. It's also called positive rate, true positive rate. What is the specificity? How specific it is? So that is given by true negative divided by false negative plus true negative. Okay, and depending on which, so if you have worked on clients where you have this kind of uh, prediction model, and then they would want okay, they don't care about specificity, they want higher sensitivity, high precision. Then you will compare the sensitivity score. Okay, or they want to compare okay, how much misclassification rate is there. So what is misclassification rate? It's given by false positive plus false negative by total accuracy, total number of cases. So these are the four parameters you can calculate, and depending on cases, you can compare the models either just on accuracy or which is more sensitive or which has more misclassification rate or less misclassification rate actually. Okay, so this is how confusion matrix is used. So any questions here? Hmm. So let's try this. So let's call it L. Let's do it right now. So what is my accuracy? So accuracy could be a straightforward calculated, but let's see what is my misclassification rate. Suppose. So accuracy L is what? TP plus TN. And my misclassification now we do the same thing for another model, which is RF. So let's run this. Let's print accuracy L F. But maybe sensitivity would be more useful. True positive, true positive plus false positive. So now you see, if I see accuracy, logistic regression model has higher accuracy rates, 82% accurate. Even the misclassification rate for logistic regression model is lower, 17.93. It's 19.7. But if I have to see sensitive, which is more sensitive, then our random forest based method is more sensitive. It's around 76.3% sensitive, whereas this one is only 75% sensitive. And in case of, yes, so you see this one is
When sensitivity is
prediction
high,
based on
it means
logistic regression.
it
This
is
is
more
prediction based
useful.
on random forest. Hello.
Yeah, when sensitivity is high, it indicates it is good or not.
Yeah, so that's based on what your client want. So in case of, suppose this was a case of drug testing. Okay,
Mm-hmm.
drug testing, they want not only good accuracy, but they want high sensitivity, that it should be very highly
Okay.
sensitive. Okay, so in that case,
Yeah.
they would maybe choose this one because this is more highly sensitive. It's 76.3% sensitive compared to 75. So though accuracy was low, the sensitivity is higher. But if your client says that, okay, I don't care about sensitivity, I just care about accuracy, then you will choose modern based on the accuracy score.
Right, right. It means in case of, for example, in data centers also, where remote infrastructure is getting managed,
Hmm.
those people will also go for example, for handling a downtime, they will go for more sensitivity, right?
Yes. So that's why I'm saying this is not
Mm.
subjective. That okay, which measure you
That's
want.
not subjective. Mm.
So in drug
You're
cases, you
right.
want higher sensitivity. So though if you see the accuracy wise, it looks like logistic regression is better. But if this, we want a modern which is more sensitive, then you can go with random forest in this case.
Mm-hmm.
But if somebody says
Right,
that okay, in our case we want high specificity, then you will calculate the specificity and then use that to compare your models. So it's not that only one parameter differentiate between a good and bad model. You have to see what they want to predict, like what is important to them: accuracy, sensitivity, specificity. So these are all parameters which you can calculate on your predictions, and then use one of them
right,
as a tool to choose a best model.
right, right,
Okay, so this is the approach
right. Got it.
confusion matrix. Now another popular one is ROC AUC curve. Okay, so this is I forgot the full form ROC. So AUC is area under curve. ROC full form. Yeah, receiver operating characteristics. So the
Okay.
full form of ROC. So what it does is actually it just plots your sensitivity and one minus specificity. So one minus specificity is also known as your false positive rate, and your sensitivity is known as the true positive rate. Okay, so where is my example? So this is how the plot look like. Okay, so this diagonal plot is your random prediction. So if I have to do a random prediction, there is a 50-50 chance of predicting either one of the classes, right? So this is what
Right,
the output you get from a random prediction, and this is your based on your sensitivity and specificity, the predictions from your learning model. Okay, now you find out what is the area under this curve. So area under the curve means this area. So under this whole area, what is the area here? Okay, the higher this area, the better is your model. So the best model would
yeah,
be
means the triangle which is getting formed, right?
no the whole this area, not just the triangle, this whole area.
Okay, okay.
Okay, so this is the area under curve. So the best model would be when your curve is like this. So when the orange line is like this and this, then it's 100% covering the area, right? That's the best
Right,
model.
right,
That means it has 100% true positive rate and it has 100% false positive rate. So that's the best case. So rule of thumb, anything you get between 0.9 to 1 is a very good excellent model. If you're so this is called
okay.
score, ROC score. So if your ROC score is between 0.9 to 1, it's an excellent model. If it is between zero point 0.8 to zero point 0.9, it's a good model. If it is zero point 0.7 to 8, it's a fair model. If it's zero point 0.6 to 7, it's a poor model. If it is less than zero point 0.5, it's even worse than random. Like it's a bad model. Generally, if it is less than zero point 0.5, what people do is they reverse the prediction. They do 1 minus prediction. So whatever is predicting, it just do the opposite. So you never get a less than 0.5, because zero point 0.5 prediction is random prediction.
Mm-hmm.
Okay, so if you're getting less than 50% accuracy, so you just reverse your predictions. So if I'm predicting that okay, he will live with error of 0.30% only, with accuracy of 30%, you just reverse your model that okay, whenever my model says live, you say it dies, and then your accuracy is 70%, right?
Right.
So you will never go below minus zero point 0.5. So calculating ROC is very easy again. So there's a function called ROC curve. So here I just plotted it, but there's a function called ROC AOC score. You can just pass your Y test and Y prediction values, and it will give you the area under the curve score, the value this. You have to just check this value is greater than, is in which range, like is it excellent or good or fair or poor. And this is also a very
Good.
good
Excellent.
characteristic
Yeah.
of your classification models. So a higher ROC AOC score means it's a very good model because it is not only sensitive but it's also specific. So it's a combination.
Which model we have used here?
For this example, we use logistic regression only, I guess. Yes, this is the same.
Okay.
So it could be used for any, because this calculates your, it's independent of the model. Huh? So whatever model you used, you get your predictions, right? So you get the score
Right.
based on your prediction, what was the actual value.
So it is indirectly telling us your prediction is how much you are accurate in your prediction, right?
Yeah, means how, not just accurate, that how much sensitive and specific you are.
Okay.
So because from when you say accurate, people only think about just this accuracy score, which is
It's
how many places.
specificity and sensitivity both.
Sorry.
It is telling us sensitivity and specificity both.
Yeah. Like, so that's why ROC is very popular. Huh? So any classification
Right.
problems, when you so what happens is, suppose you have a model where you have to, your training data, suppose in training this Titanic data, okay, suppose you had only 1,000 rows. Out of this 1,000 rows, 9,000 rows has only one model saying, or 9,900. Okay, so suppose there were 1,000 entries. Out of this, 950 are dead and only 50s are alive. This is
Right.
the input data. Okay, and your model comes up with that, okay, irrespective of what happens, everybody is dead. Still your accuracy would be very high, right? It's 95% accurate.
Hmm.
But this is not a good
Right.
model, because when you see the
Not a
ROC
good
curve,
one.
it would be not very good. So that's why
Right.
just going by accuracy is not always good. That's why you try different
Hmm.
other parameters.
Right.
So these two, confusion matrix and ROC AUC curve, these are two of the most popular ones which are used for comparing classification algorithms. So if you know
Okay.
specifically, if I have to check for sensitivity, or if I have to check for specificity, or if I have to check for misclassification, then you can calculate it using the confusion matrix. Or if you
Right.
don't know that and you just want to see, okay, which one is a good balance between specific and sensitive and everything, then you can go for ROC AUC curve.
Right. Right.
Okay. Now some people also use Gini coefficient.
These are new statistical terms, or these are well
So these
uh,
terms came
there
before even the
within our
machine learning comes. These come from your statistics actually.
So it means this is not something which are new statistical terms. This has been taken out from statistics from which was
Yes.
there earlier
To
also.
evaluate your predictions. So if you go into more complex terms, so there are some. So these terms which we talked about,
Proficient. Hmm.
the gain and F chart, KS chart. So these are all very old statistical tools. Okay, which
Uh-huh.
was used to evaluate how the samples are related and how when they represent your true values and all. Okay,
Right, right. I studied statistics till class 12th. Uh,
so nobody
I was
studied
having
the statistics.
commerce background.
So we'll just touch
There we
upon.
just studied correlation, variance, standard deviation, and all these things, but not more than that. In MCA, we did somehow, but that was also just to pass it out.
Okay. So similar to ROC curve, there is a something called Gini coefficient, which is nothing but two
Mm-hmm.
times your AAC score minus one. Okay. So this is
Okay.
actually the area between this triangle area. That how much better it is from a random prediction.
Yeah.
So this triangle area is your Gini coefficient.
Okay. Okay. So 2 into AUC minus 1.
Yeah. So and it says
That is
that
the
if you have
formula.
a Gini score of more than 60%, it's a good model.
Okay. It is again basically checking the area, but it is only specifically to the triangle.
Yeah.
Okay.
Okay. So some people prefer ROC curve. Some people say, okay, what is the Gini coefficient? So these, if you somebody asks you, it's easy to calculate. So AOC is 2 times AOC minus 1 is 0 Gini. You can get that. And so if it is more than 60, it's a good model. So there's lots of
But how
statistics
the
behind it, which we don't want to get into. But
but here we simply written this, but how AUC is derived?
so AOC is this. There's a function called ROC AOC score for which you pass your
Okay. Okay.
test, your prediction, and it will give you the score.
Okay. Okay. So ROC right now is basically having AUC, right?
So
In
ROC
variable ROC,
plot, this line is your ROC, this is the curve,
right?
and AUC is the area under this curve.
Right.
Okay, so that's why it's called ROC AUC score. The area under the curve, which curve? This ROC curve.
That is fine. But in Gini coefficient, we have formula where we are taking AUC only.
And so this is
So
actually ROC
how?
AUC curve. So it's
Okay.
okay.
This is ROC AUC. Okay.
Yeah.
Okay. Got it.
Okay.
Mm-hmm.
So
Right.
there were few more topics like gain and lift charts,
Yeah. Let's
yes,
do it in next
concordant
class.
discordant ratios, but I don't think we have time. We'll do this next week. Okay.
Right. Right.
So these are some statistical tools which are used in specific cases, mostly in
Mm-hmm.
marketing cases, to evaluate models. So we'll check
Right.
in the next week. But for
Sure.
classification problems like what we saw recently, it's mostly you will be using either confusion matrix or the AOC ROC curve.
ROC. Right.
Okay.
Right. Right.
So let's end for today. So you are the only one which are in the class. So just share the feedback. I think the link is same.
Yeah. Sure. Yeah. Please share with me again.
And then so next week I think everybody will go through a recording. So I will just say for the statement that okay, next week we'll do the remaining three uh, models for evaluation, which is the statistical model, Gini-F chart, KS charts, and concordant discordant ratio. And we'll start the capstone project. Okay.
Okay. Okay.
Okay. See you the next week.
Good. I have given you the feedback.
Thanks.
So Rohit, like at present, you are